Okay, as I've been introduced, I'm Bo Farmer, and I'm on the faculty in the physics department at New Jersey Institute of Technology. We're not really a new department, but what we do have that's new is an applied physics program, and one of our strong suits is a microfabrication and cleanroom facility, and I've been there for the last 4 or 5 years doing research in thin oxides on silicon and also in wafer bonding. And today I won't talk about wafer bonding or any of that, although if anybody's interested in MEMS or SOI or SOS type power applications things, we can talk about that. But instead I'll be talking about thin oxides on silicon and my research in that area. And the title, which you see here, is Positive Charge Generation and Breakdown in Ultra-Thin Oxides on Silicon. And I hope by the time I've finished, I've challenged a few of your notions about breakdown in really thin oxides. And I hope I've convinced you that while thin oxides aren't the answer to all the problems that you see in thicker oxides, there are some really exciting possibilities that maybe we should start considering using really thin oxides. People who've worked with me are a postdoc at Fort Monmouth, New Jersey, working with Dr. Poindexter and myself, Christophe Deboche, and an undergraduate student who's worked in my lab, Alex Giordano. In addition, I've had nice collaboration with the people who I worked with up in Sweden, Per Lundgren, who's finishing his PhD, and Mats Andersson, who has received his PhD a few years ago. And I have bad news, he's leaving our field. He's a really bright guy. This doesn't tell you what the future is for our field, but he's going on to Volvo. And so any of you who grew up and own Volvo cars, the sensors, he'll be responsible for those. And then also Doug Buchanan, he's at IBM Research Center and has been supplying devices to lend some industrial relevance to the research. And the work is sponsored in part by a grant from NSF, which will be ending quite soon. Here's an introduction for the talk. There's a debate in the literature right now. The debate's between me and my collaborators. And that is, well, we know that Fowler-Nordheim stress leads to defect generation in thick oxides, and by thick I mean anything greater than 3.5 nanometers. But there are conflicting reports on whether direct tunnel stress really leads to defect generation or not. I say it does. Some people have put some papers out in 94 and 95 saying that they don't see that, but it's because it's a subtle effect. I believe, in fact, the defect generation that I see is sort of the principal degradation mechanism in oxides that are less than 35 angstroms, and we'll talk about that. That's the focus of my talk. And I hope, if nothing else, I've convinced you of the bad news that, yes, you still have to be worried about defects in direct tunnel oxides. So I'm going to report then a study of this direct tunnel defect generation as functions of some of the parameters that you can vary in MOS capacitor structures: bias voltage, oxide thickness, electron fluence, how many electrons pass through the device for this time-dependent degradation. Varying the temperature turns out to be extremely important for understanding the mechanisms. So that people take you seriously, you really have to consider devices that have polycrystalline silicon gates, but it turns out the effect can also be seen in aluminum gate devices as well. I'll talk about gate injection from the gate and also from the substrate using N-type silicon, and a range of oxide thicknesses, which leads to some pretty surprising findings. And finally, I'll talk about the relationship between this positive charge and the ultimate demise of the oxide. If there's a relationship between these, then this is particularly an interesting area to be doing research. So first, experimental details. This is just a picture of a capacitor structure that you're all familiar with. Silicon substrate, a thick field oxide, open a window in the oxide of some area all the way down to the silicon, reoxidize the silicon interface, and then deposit some gate metal, aluminum or polycrystalline silicon. I say here that we're looking at N-type silicon. In that case, you'd have to put a positive voltage on the gate so that you have electrons being injected from the silicon towards the gate. But also I'll talk about data where you use P-type silicon. In that case, you put a negative voltage here and you inject electrons towards the silicon, and I'll talk about damage that takes place for both types of injections. The device size that I'll be talking about, D, the diameter of the device, is 250 microns, which is a pretty big area, but I've also looked at devices down to a micron square or even smaller, and I'll tell you about some results comparing larger area with smaller area devices. And again, the thicknesses range from 13 to 34 or 35 angstroms. The simplest way to characterize these devices is measuring current versus voltage. So what I'm showing here for polycrystalline silicon gates, and this is for a while now I will be talking about the case where you inject from the substrate. This is a plot of current density, amps per square centimeter, versus gate voltage for the different thicknesses, for a thick oxide, for a thinner, and so on. And what you see, this ranges from 13 angstroms to 35 angstroms. Roughly speaking, the current increases by about a factor of 100 for every 4 angstrom decrease in thickness, which is in good agreement with tunneling theory. And this is the first order approximation of how you characterize the devices. As you say, on average, these oxides are roughly some thickness, and since that's 3 or 4 angstroms, or 2 or 3 orders of magnitude here, that's 3 or 4 angstroms thickness difference. And so roughly speaking, this is a measure of the thickness of the oxide.
So that's the plot for 35 angstrom oxide?
Yes.
Is for that flat region there, is that the limit of your...
Yes, that's just the limit of our measuring capabilities, 10 to the minus 14 amps or something like that. We can't measure the current any smaller. This is current density. So we use a HP 4140B, and supposedly it has femtoamp resolution, and that's about as, we have low noise system, but that's as low as you can get. Presumably the current just falls down. I want to give you a schematic band diagram then of the electrical stressing conditions for both Fowler-Nordheim, which most people who've dealt with thicker oxides is familiar with, and direct tunneling, which is what I'll be talking about. In the Fowler-Nordheim case, again for substrate injection from the N-type silicon over towards the gate, this isn't exactly drawn to scale, but the conduction band of the silicon is where the electrons come from, and they're injected into the conduction band of the oxide. They're then accelerated, if there's any field for them left to be accelerated, and eventually are thermalized in the gate material. In contrast, there's injection in the direct tunneling regime. If the oxide is thin enough, electrons are injected from the conduction band all the way through the trapezoidal barrier of the oxide and never have to enter the conduction band of the oxide. And what people in the literature say is, well, because these are 2 different injection conditions, hey, you don't see any damage if you don't go in the oxide conduction band. That's not correct, as I hope to show you, that we definitely see damage even if you just tunnel directly through the oxide. The electrical stress that I'll be talking about for substrate injection has been performed always in the direct tunneling regime with a gate bias of less than or equal to 3 volts. Okay, so I want to start right out with an instability. Call it direct tunneling degradation. What I'm plotting here is the fractional change in the current versus time. Now, if there's nothing happening in these oxides, you sit at a constant voltage, and what happens to the current? Nothing. Nothing should happen to the current. But instead, what we see is that the current is gradually increasing over time. You take the current as a function of time, subtract the initial current, and normalize by the initial current, and you see that after about 10 to the 4th seconds, there's a 2 or 2.5% change in the current. It's a subtle effect, but the current is gradually increasing. And we interpret this as an increase in positive charge. If you increase the positive charge in an oxide, an easy model that you can do is you say you're creating a sheet of charge in the oxide. That isn't necessarily what's happening. This modifies the barrier for tunneling. It decreases it. And so you have an increase in the tunneling current. In fact, the modification of the barrier is, let's see, it's, I lost myself there for a second. If you, I'll come back. It's something that happens to me sometime. Let's see, you're modifying the tunnel barrier. What are you doing? Okay, I got it. You modify the tunnel barrier, so what you're doing is you're allowing it so you have an increased current passing through the device. The fractional increase in that current is the same as if you had a certain amount of charge that's being created in the oxide. This comes about from theory. I've done the calculations and I actually presented this 2 years ago. What I want to say here is that the fractional increase in the current is like a measure of the charge that you're creating the oxide. But that's not the only interpretation for this. For example, you could also say that you're creating some tunneling center. But in any case, you're creating some change in the oxide. I think you have to agree, whether it be a defect that acts as a tunneling center or it's just some charge in the oxide. I'll call it charge for convenience. So there's, anyway, some sort of change in the device characteristics over time. This is substrate injection at constant bias. Fractional increase in the tunnel current versus time is analogous to creation of charges or creation of defects. And I don't know if you can see this on the screen or not, but what I've put here is the time and the corresponding amount of fluence, or the number of electrons that have passed through the device. Like 0.17 seconds, there's about 10 to the minus fifth coulombs per square centimeter. Not much fluence. But after 75,000 seconds, there's a tremendous fluence that's passed through, 15.2 coulombs per square centimeter. And you know that charge to breakdown numbers typically in oxides 1, 10 coulombs per square centimeter, but you've also heard rumors about how as you decrease the oxide thickness, the charge to breakdown increases exponentially. Have you heard about that? That there's a really strong increase, and I'll be addressing that later on, but clearly you can put a huge amount of electrons through these devices. I want to talk now about sort of the characteristics of this defect creation or direct tunneling degradation. I want to show some properties of the effect. For example, there's a threshold voltage for the turning on of this effect. I'm applying the fractional change in the current measured at a particular time, 1,000 seconds, versus the bias voltage that we sit at. The previous foil I showed you, we were sitting at 2 volts across the device. So that would be right here, sit at 2 volts, and after 1,000 seconds, there's 20–25% change in the current. But if you sit at a lower voltage, you have lower. You know, the voltage is just change in the rate of defect creation. You have maybe 1% change in the current after 1,000 seconds. Sit at 1.2, it's even lower. At 1 volt and at 0.8, for example, we can't measure, even after sitting for several weeks, not just 1,000 seconds, we can't measure defect creation anymore. And that's why I show in this lower plot here. Fractional change in the current versus time sitting at 1 volt on a 28 angstrom oxide, and it just doesn't change. There's a threshold. It's about 1 volt for the creation of this damage. If you don't put 1 volt across the device, you don't create the damage. So now here's what the people in search of the Holy Grail, the indestructible oxide, say. They say you have if you don't do injection into the oxide conduction band, you don't create defects. That's not correct. There's still good news. There is a region where it appears you don't create defects, but it's not that 3 or 4 volts, it's 1 volt. It's a 1 volt bias across the device. Now I've been talking about polycrystalline silicon gates threshold. Here's a huge plot that almost fits onto the screen. There you go. Fractional change in the current after 1,000 seconds of stress versus applied voltage. The same thing, but this time it's aluminum gate. And it's the same sort of effect. At high voltages you get a lot of this defect creation. At lower voltages you get less, and it's turned off at about 1 volt and below. You don't see the defect creation. This is pretty exciting. That means that there really is opportunity. If you ever get to a case where you're not putting more than 1 volt across the oxide, you're not going to damage it. And if this damage is related to destruction, that's really good news. There's not a lot of people out there who understand that. And so if you shake your head and say, yeah, this is neat, that's really great because you're seeing, I think, the future of the silicon industry. There's also an interesting effect that goes right out here. It's above about 1.8 volts. You actually see a decrease in the current. It's as though there was negative charge being created or something. And it's well known that there's relationships between positive charge creation and negative charge creation. Something else is happening here, which I'm not going to get into. And also, one other thing I want to point out is that there's 8% change in the current instead of 1 or 2. Aluminum gate devices, there's more of whatever this defect is, more precursors for it in the aluminum, and that's well known too. So it's better to look at polysilicon, but it's much more subtle effect in that system. Okay, I'm getting back to polysilicon gate devices, and I want to look at the thickness dependent of charging. And this is what I promised you in my abstract that I sent you, and it's the most surprising finding, and I hope I can get it across to you because it has implications for how you quantify breakdown in really thin oxide devices. Fractional change in the current versus the stress voltage. For 3 different thicknesses of oxides, 34 angstroms, 28, and 24 measured at room temperature, and this is after 1,000 seconds. You're familiar with these types of curves. Yes?
Plotted this versus, instead of having a constant time, but maybe a constant fluence, would it change the plot?
Well, this is the point of this foil. Just watch this, and I think you will see what the point is. Help me out here, and that will help everyone understand that. If I have a 3.4 nanometer oxide, am I going to have more or less fluence after a given amount of time than a 2.4 nanometer oxide? Way less, right? 5 orders of magnitude less fluence for the 3.4 nanometer oxide than compared to the 2.4. So if fluence, the electrons, have anything to do with the creation of the defects, or if at least they have anything to do with the rate-limiting mechanism for the creation of the defects, then you would expect that where you have more electrons going through, you have a greater rate of this creation of the damage. You would see a greater increase in the current passing through the device. But instead, what we see is that the 2.4 and 2.8 nanometer oxide data is kind of indistinguishable. Plotted, this is after 1,000 seconds of time, at any voltage, say we sit at 2 volts, we're going to see the same amount of damage in the 2.4 and 2.8 nanometer oxides. We're not seeing 5 orders of magnitude difference in the degradation or in the creation of these defects. We're seeing hardly any difference at all. The biggest difference we see is when we look at the 3.4 nanometers, there must be some transition or turning off of the effect, but we see a little less, maybe a factor of 2, no more than a factor of 10, and I'm being way generous there, but certainly not 5 orders of magnitude change in the defect generation rate. Let me just say it again so you can read it and to have it sent in. Fractional change in the current is bias dependent, but it's not strongly thickness dependent. For example, the fractional change in the current is the same for the 2 thicknesses, the thinner thicknesses, and it's a little lower for the thicker thickness, but not that much lower. And if you looked at different times, you could make similar curves. And I'm pointing out also that this is analogous to previous findings in gate injection studies, and I'm going to show you some of those findings so that you'll be convinced that this is something very interesting and universal. Brian and I were having that discussion just now. You look at different thicknesses of the oxide and measure the current or current density, say at some voltage, and there's, say, 5 orders of magnitude difference in the current density. But there's hardly any difference in the defect degradation that's taking, generation, or the degradation that's taking place. Fluence through the oxides of different thicknesses differs by nearly 5 orders of magnitude, but the corresponding fractional increase in current at a particular bias varies by no more than that factor of 10, as I just showed. That means, and this is the salient point of this part of the talk, is that degradation from substrate injection is at best weakly dependent on electron fluence. The analogy I use with my students is I could punch you in the arm 1 time or 1,000 times in a given amount of time, and you would still only have 1 bruise. In other words, those electrons aren't what's limiting the bruising mechanism or the defect generation. Something else is, and it's controlled by the voltage. Let's go on and look at some other characteristics now. That's a big deal, by the way. I'm going to say it again before I'm finished, and then I'm going to interpret it for you. Defect generation temperature dependence. It's important to look not just at room temperature. You might learn something. Fractional change in the current versus bias voltage. Curves that you've seen again and again, measured at room temperature for 2.8 nanometer oxide, measured at 240 Kelvin, and then measured at lower temperatures. Certainly you see that the defect generation rate decreases drastically with temperature. And also, if you look the difference between this and this is very large, while the difference from here to here is kind of small, there may be some sort of transition in this temperature dependence at lower temperatures. And let me elucidate that further with this plot. Defect generation temperature dependence. Again, this time I'm plotting fractional change in the current, or the amount of charge created, versus 1 over the temperature, 1 over kT. So this is a suggestive of thermal activation. It's an Arrhenius plot. And what you see is this line right here is about 150 degrees Kelvin. Above 150, that's in this direction because it's inverse temperature, you see thermal activation with about a 0.02 eV activation energy. And below that temperature, you see not much temperature dependence at all. And this is for 3 different thicknesses, different bias voltages. It's a general property of these devices. Thermal activation above 150 degrees, weak temperature dependence below 150, analogous to findings that I'm going to show you with the gate injection. Remember, this is all for substrate injection. I want to give you some conclusions. These are intermediate conclusions. Just people pay at most attention when you put a foil up that says conclusion, so I have a lot of those. Significant increase in current or defect generation during electrical stress in the direct tunneling regime above a threshold. So defects are created. The battle between whether or not they're created, I think we're winning. It occurs both in Fowler-Nordheim and in the direct tunnel regime, but there is this 1 volt threshold. This effect is weakly dependent on the fluence. That's being conservative. I don't think it matters, but maybe I don't even think the electrons are important, but that's a matter for discussion later. It seems that defect generation evolves in time rather than with this fluence. And now people who've done Fowler-Nordheim studies always say fluence is important, fluence. I say this is a time-dependent effect. As far as the temperature dependence, it's weakly dependent on temperature at low temperatures, thermally activated above this temperature, and similar to findings that I'll now talk to you about for positive, for p-type silicon or for injection from the gate. So now I want to just fly through. You've seen it all before. You just saw it. And I hope that's what you say. You've just seen it for injection from the substrate. Now I'm going to show it to you for injection from the gate. In that case, here's the gate here, here's the silicon, and injection takes place. For example, there might be some voltage so that you have injection happening right here. Never into the conduction band of the oxide. It's just the opposite picture. And what I'm showing here is the same thing. It's not fractional change in current. This is absolute change in current versus time again. And there's actually 2 effects that take place. You have to put a negative voltage on these devices, in this case, in order to get the injection from the gate into the silicon, not positive. And above a certain voltage, whatever that is, I'll tell you in a second, you see a gradual increase in the current. But below that, you see a decrease in the current in aluminum gate samples. I've now learned how to get rid of that. That's some water-related instability, which I've talked about in the past. And it doesn't show up in polysilicon gate samples. And what I'm mostly interested in is the thing that just doesn't go away. It's this positive charge generation, or this gradual increase in current. The first thing I want you to notice is that there's a threshold again. But this time, it's whenever this voltage right here is about, or 2 electron volts. That energy is about 2 electron volts. In other words, an applied bias of about 3 volts. So for substrate injection, the voltage threshold is about 1 volt. For gate injection, it's about 3 volts. And I have to tell you, I can't see what's the same about those. There's something weird there, and I would like any help that students or faculty can give me in understanding what would be the same. I have some suggestions. But anyway, these seem to have, this injection mode seems to have a threshold as well. Okay, that's enough for that. I didn't say this previously, but this is an obvious point. People have talked about how the field is important. You know, the electrons, the field, all that, that's important for degradation. But this isn't, definitely not a field. I don't even think it's an electron energy threshold, as I say on this foil, because it's an old one. But it's definitely not a field effect. Think about this a second. In one case, you have an amount of damage that's being created, and you have, say, 3 volts across a device, and the device has a 20 angstrom oxide. In another case, you have the same 3 volts across the device, but now you have a 30 angstrom oxide. Is the field across that oxide the same? Nowhere near the same. For example, if we compared the 13 angstrom oxides to the 26, we'd be doubling the field, assuming that we weren't having much voltage drop across the silicon. You don't have much voltage drop across the silicon for substrate injection. In the gate injection case, you do have about a volt across the silicon, but not, but that still doesn't make it, that's not different if you change the oxide thickness. So the point is, this is not a field threshold effect. That's all I'm going to say with that for. Now, remember, okay, this is published in Applied Physics Letters. We were talking about gate bias and oxide thickness dependence previously for the substrate injection. This is the same effect. I'm looking at it a slightly different way with this graph here, plotting fractional change in the current versus time. And so you just see a gradual increase over time. This is for one device. Each one of these curves is for one device, except that it's really for 2 devices, open circles and closed circles, or open squares, closed squares, open triangles, closed triangles. The difference is that the filled symbols are for the thick oxide that we studied in this case, 32 angstroms. The open is for a thin oxide. And what you see is the degradation, or the fractional increase in the current, or the charge that you're creating, is about the same independent of the thickness, despite the fact that, as this chart over here shows, the fluence in one case is measured in amps per square centimeters. The fluence in the thick oxide case is measured in microamps per square centimeters, about a 5 order of magnitude difference in the current passing through the devices, because there's a 5 or 6 or 10 or 12 angstrom difference in the thickness of the oxides. And yet, the charging that's taking place is independent, apparently independent of that fluence. I'm making this such a hard selling point here because people just don't believe it. And it's a fact. We're going to have to live with it. And I'm going to show you how it manifests itself probably in some of the data that people have been taking in industry, and they're just refusing to interpret it right, as far as I'm concerned. There has to be at least one step, maybe 2 steps. But one thing's for sure, that the electrons aren't the rate-limiting step, aren't the controlling cross step. If you force the electrons to be involved, then the rate-limiting step for the creation of defects is something that's controlled by the voltage. Increase the voltage, you increase the damage that's taking place and the rate of damage. If the electrons are forced to be involved, then their energy has to somehow be deposited, but that's not what's limiting the rate. And I have to tell you, in one case we have a 1 volt threshold, in the other case we have a 3 volt or 2 electron volt threshold because the 1 volt dropped across the silicon. Even that becomes a little dubious. I don't believe necessarily that there's a threshold for, that there's electron energy involved at all. Let's look at the temperature dependence. Again, this is for injection from the gate. I'll just go to the graphs. Here we have log of the fractional change in current versus 1 over kT, Arrhenius plot. At low temperatures, it's kind of flat, kind of noisy for aluminum gate devices, and exponential increase at high temperatures. And for polycrystalline silicon gate devices, kind of temperature independent, low temperatures, exponential at high temperatures. And it's about 150 degrees Kelvin is where there's some turn on of this thermal activation. What kind of effect how can you describe this? I want to tell you about a paper I saw in Journal of Applied Physics where some people were trying to really stick with an IBM model where there's some diffusion of neutral species, and they said, oh, that must be taking place at high temperatures. After all, diffusion's thermally activated. That's what we're seeing at high temperatures. And oh, well, let's come up with an entirely different model or mechanism to explain what's happening at low temperatures. But let's not relate it to the we've got to hold on tight to this neutral species diffusion thing because some very important person thought it up. And so we'll hold on to that and just come up with a whole second model for the low temperature. Now, to me, what I would say is let's have one mechanism for both temperature regimes. And I'll give you one that I'm familiar with. You need what's called a configuration coordinate description for a defect or defect precursor. Now, think of a defect precursor as, say, a silicon-hydrogen bond. The hydrogen atom is like a mass on a spring. And so you use a harmonic oscillator approximation, and that's what this is here. This is the energy, vibrational energy of a harmonic oscillator. in some energy state. And this is the electronic plus vibrational energy because you can reference it to some electronic energy. So you've got a defect that's in a state, and the 0 here means that it's in its neutral state. Now what it does is it becomes a defect when it makes a configuration change. This is configuration coordinate here. It makes a configuration change which may or may not be accompanied by a change in charge state. In this case, I believe it would have to be accompanied by a change in charge state and make it a positive charge. So you have a new harmonic oscillator, a new relative electronic energy, and you can reference that to the valence band. In that case, you would say what you're doing is you're capturing a hole. You've got an electron coming from the silicon valence band or going to the silicon valence band, a hole coming into the defect. And so what you do is make a transition. Now, the way you think about transitions is you are vibrating in this configuration. If you have enough energy to make it to this point, you don't know what configuration you're in. You can make the transition depending on probability issues. So you make this transition down to this state here. And if you make this transition, if this is a lower energy, a particular temperature isn't enough to allow you to go back into this state. It's kind of an irreversible process, at least at the temperature that you're looking at. And in order to get this vibrational energy, that's temperature. You need to be thermally excited. So you've got thermal activation at high temperatures, and if it's a defect that's in close proximity to the silicon surface, you could have tunneling, either tunneling of the electron or configurational tunneling at low temperatures. And that, I believe, is what's taking place. And this is stuff I studied for my PhD thesis a long time ago, and that's the information I bring with me into this field, is that I think a model like that is more appropriate, though I'm just beginning to come up with the model for what's happening. Now let me summarize positive charging up to this point. It's a wake-up call, one of two more after this. It occurs for either substrate or gate injection. Doesn't matter whether it's aluminum or polycrystalline silicon gates. Samples can be made at different facilities. This is a universal effect, and I believe it's the principal instability that we have to be concerned with when we go to ultra-thin oxides. Very similar voltage dependence in all cases beyond the threshold, although there's a 1 volt threshold in one case and a 3 volt or 2 electron volt threshold in the other case. Very similar fluence dependence, very similar temperature dependence. As you just get the feeling there's something important here. And again, here are the two different thresholds, which I think is a key to understanding what's happening. More positive charging data. Just a little more, just to frame the process. You can look at the noise that's associated with the positive charging. I studied in my past history something called two-level fluctuations, where you plot the current versus the time. Like during, you watch it on an analog recorder or going across a digital oscilloscope screen. And this is what the noise looks like. This is just a picture of the noise after a little while of degradation in one of these devices. And this is a picture of the noise after longer. The noise is changing its character. That's all I want to point out. And you can actually measure this. It's a noise increase. But it's consistent with the creation of defects. That's what I'm trying to say. So if you didn't believe defects with my hand wavering and stuttering before, this helps. Since this occurs in both aluminum gate and polycrystalline silicon devices, now that we have have been validated by finding it in polycrystalline silicon, people will believe us. Now we can go back and look at some aluminum devices and take advantage of something that you can do there. You put aluminum down and don't post-metallization anneal, you've got one quality of oxide. You anneal and you change the quality. And so you can look at annealed and unannealed oxides, as grown, I say, fractional change in the current versus time. In annealed devices, check this out, you can get as much as 100% change in the current if you sit for a certain amount of time. And these dots lying over top of each other, remember, that's the different thicknesses. Whereas in as-grown oxides, you can't get anywhere near that amount of change in the current, much less fractional change in the current. So that may mean much less charge. And if that's what that means, then that means that the annealing species is involved. Although there's an alternative interpretation which means exactly the opposite, and so I'm still not going to make any claims other than it's possible the annealing species is involved. There's something related to annealing.
What were annealing conditions?
I'm glad you asked the question. When you do annealing of aluminum gate samples, A lot of people want to do annealing in forming gas, 450 degrees, 10, 15 minutes. That's not the right way to do it. The studies show, one study in particular by, I can't remember, it was a few years ago, shows that 300 to 350 degrees for 10 minutes is the optimum annealing. You can even get annealing at 170 for longer, but if you go higher than that, you get some sort of a reverse annealing effect, and you over-anneal. But that's specific to aluminum gate devices. You can do it in forming gas, you can do it in nitrogen, you can do it in air. It doesn't matter when you have a field oxide surrounding the device, because hydrogen, which is responsible for the annealing, isn't going to go through the aluminum. Hydrogen comes from the oxide aluminum interface. It's a water-related species there, and it's freed up. Peter Bach showed this in '66, and that's where it and although people kept saying, oh, hydrogen has to come in from somewhere, it doesn't. It's already in the oxide. So yes, I did it in forming gas, but I also did it in nitrogen. And I have to confess, I've also, in a pinch, done it in air, and it just doesn't matter as long as you got the oxides sealed. And it's 350 degrees. I got a whole paper on that, and I'll be glad to show you. This is the last bit of positive charging data I'm going to show you, and then do a little summary, and then talk about the relationship of this to breakdown, and I'll be done. It's a possibility that the defects that we're creating are localized in energy. You know, you want to measure interface state density, but you can't do CV on these, but you can use current voltage characteristics. It turns out for injection from the gate, the current voltage characteristics don't look anything like the monotonous type of IV characteristics for injection from the current. That's from the substrate. That's because for injection from the gate, you've got a region where you're sweeping through depletion in the silicon, and when you do that, you have to drop your voltage across the silicon and not the oxide. So theoretically, you don't expect much change in the current passing through the device while your voltage is going across the silicon at that point. But then you expect a strong turn-on of your tunneling current. Well, devices I make nowadays, I can make curves that look just like this using aluminum gate. But in the olden days, here was an as-grown sample, and here's a positively charged sample, one that had been stressed, IV characteristics. And this is particularly sensitive to defects. And you can actually extract a kind of an interface state density curve, though you don't know whether these are charged defects or current trap-assisted tunneling defects. But in any case, you can locate them with respect to surface potential. So here's a nominal number using a sheet charge calculation, a nominal number for interface states versus surface potential before charging and after charging. And you see that they seem to be localized about 0.3 of an electron above the conduction band edge, kind of like where PB is located. But I'm not going to name it. I'm just going to say that you're creating some well-defined defect. Okay, final summary here. By putting all this stuff together, you have the nature of the defect. Here's what I know. That noise tells me it's a defect. Current voltage characteristics tell me it's at a well-defined energy. I've also done conductance measurements, and I know that there's character of both tunneling centers and charge centers at well-defined energy. Post-metallization annealing suggests that that an annealing species may be involved. Maybe what we're doing is breaking a silicon-hydrogen bond. The mechanism for this, it occurs by some sort of tunneling process. That's what I showed you in the configuration coordinate diagram. At lower temperatures, it's thermally activated at higher temperatures. I don't necessarily believe anymore that a kinetic energy threshold is involved. That I don't even know if you need these tunneling electrons per se, at least for the direct creation of the defect. Instead, there's some time evolution process, and that's what this defect creation is, where the rate limiting step is controlled by the voltage and not the fluence. Now I want to go to breakdown. We've been looking at a really interesting instability, but now let's ask this question: is this instability related to breakdown at all? I mean, breakdown is what you really care about, are these devices going to last? The instability maybe you can live with if it never goes anywhere, if it never does anything. Creating defects is bad, and maybe it'll change parameters of MOSFETs. I mean, there's a whole field to be looked at. Once you now know about this effect, you want to study that. But what I can address right now is breakdown of the oxide. For example, if you can eliminate this positive charging, then maybe you can eliminate breakdown if the breakdown is related to the positive charging. And certainly you can. Just stay within that threshold window. Don't put 3 volts across the oxide in one direction, 1 volt in the other direction. And then perhaps you can eliminate the positive charging. If the positive charging is related to breakdown, you eliminate that. And beyond the threshold, let's say you really have to sit above the threshold, how do we predict the lifetime of the device? Now what I say is that you have to watch this time evolution process. I don't have any foils for this, so we have to use our heads here. If you have a thicker oxide, you have a small amount of current passing through for a given time. If you make the oxide a little thinner, you exponentially increase the amount of current that's passing through the device, or the fluence, or the amount of Q, charge, that passes through the device. But breakdown, if it's related to positive charging, it's just something that evolves in time. You sit for a certain amount of time and then you have the breakdown, if that relationship is true. I'm just whetting your appetite. So what you would measure if you're measuring QBD is an exponential increase in QBD with thickness. But the mechanism for that, or the reason for that, is because breakdown itself is related to this positive charging, which is something that just evolves in time. And you're trying to ascribe charge onto a process that charge doesn't control at all. So you would see an exponential increase in the QBD, but if this charging is what underlies the breakdown, it's just something that evolves in time if you're above the certain bias. You understand what I'm saying? And so this is a very important point, and we really have to we have to ask the question, well, tell me, Dr. Farmer, is this positive charging related to breakdown? Well, okay. What you would expect then is you sit at a certain voltage, and the time to breakdown should be constant, independent of the thickness of the device. Now, the first thing I'm going to show you is some bad news, but then I'm going to show you some good news later on. The question is the time to breakdown independent of the thickness at a given bias. If you sit at a certain bias, you wait a certain amount of time, then you have breakdown, then that means this positive charge is most likely related to the breakdown. So here I plot stress voltage versus breakdown time for 3 different thicknesses. Let's say we sit at 2 volts. On the thinnest oxide, in 10 seconds, the device breaks down. Now this is an average of about 20 devices for each one of these points. But if we look at the 28 angstrom oxide and we sit for 10 to the 4th, that's on average, before the device breaks down. This is bad news. This says these devices seem to be breaking down dependent on the fluence or the current that's passing through. It's not independent of this thickness here. You go to thicker oxides, they last longer because you have less current going through them. At least that's what it's seeming to say, is that there's no relationship between this thing. What I would have expected to see is at a particular bias, independent of the thickness, these curves should just lie right on top of each other. But that's not what we see at all. So to first approximation, we'd be a little worried, but not really. What you need to do is get a lot of devices and do statistics and say, wait a minute, are we looking at a defect-related process or something that's intrinsic, dependent on the oxide itself? And it turns out we're looking at a defect-controlled breakdown. Now these are IBM devices, but they're large area, remember, 250 microns by 250 microns. I apologize for the smallness of this. I'll read you what it says. This is essentially the number of breakdowns that's been normalized, so I can do some probability. And this is the time to breakdown divided by 10. So this is 340 seconds, 10 seconds. And what we see is a lot of devices break down at a short period of time. And actually, some devices tend to break down longer, like 100 seconds as compared to 10 or 20 seconds. And a few devices make it long. This is defect control breakdown, if I ever saw it here. And in fact, you can just use try to apply Poisson statistics and say, well, you got one breakdown with a mean time of 10 seconds and one breakdown with a mean time of 100 seconds. And the curves just fit right on there. We've got statistically controlled breakdown effect that has to do with the defects. You've even got a whole spectroscopy here. You can say, oh, you got one type of defect here, one type of defect here, but nobody cares because you want to look at intrinsic device. So what you got to do is change the area. Defect densities are tens per 100 square microns or so, but if you can get down to 1 square micron or 5 or 10 square microns, you may see no defects at all. And maybe what you'd expect to see is longer time, certainly more than the 340 seconds here, and hopefully they would all pile up at the longest time out here somewhere. And plotting on a Weibull plot, or Weibull, probability, a log of a log versus log of time, this slope here is about 1, and you start getting a upturn right here, but it's just a modest upturn. This is a typical Weibull distribution for defect control breakdown, and I'm going to show you from Wolters and Vandershoot's paper in Phillips Journal of Research about 10 years ago. Right here is a plot that has, for defect-controlled breakdown, this is time here, time-dependent breakdown. And this part is a slope of about 1, defect-controlled, and then it turns up. And this is the intrinsic. So what you want to do is you want to study either the breakdowns in the intrinsic regime only, or you want to create a good oxide where you have only intrinsic. And one way to create an oxide where you have only intrinsic is just to decrease the area, so that you're getting rid of those defects. That's the easiest way. So what we've done now is we're looking at some small area devices that were on our chips from IBM, 1 square micron and below. And I want to show you finite lifetime of a graduate student, 4 data points so far. Number of devices, time, 200 seconds, 300. By here, all of the larger area devices had already died. 4, 5, 6. Here it is, way out here. 1,500, 1,600 seconds. I believe finally we're looking in a regime where we can see intrinsic breakdown by looking at small area devices. And I can't wait to get back and harass my students for more data, particularly voltage thickness dependent. Because if other thicknesses last 1,500 seconds as well, then finally we see that breakdown and positive charge are related to each other, that we really are looking at a fundamental effect, a degradation effect in the oxides. And if that's the case, then I'm really excited, and my hypothesis, this interpretation of QBD is correct, that breakdown above the thresholds is just a time evolution effect. Here's my final summary. This is the last summary you sit through. If you pull that back just a little bit, there you go. I believe that positive charge generation in ultra-thin oxides is universal. It's something that you'll see. Brian's going to be doing an IV characteristic for me today, or IT, and hopefully we'll see it, and I expect to. And I think it's the principal degradation effect in ultra-thin oxides. And I believe the threshold is a real key. Understanding that is a real key to understanding the ultimate nature and origin of the positive charging. And finally, positive charging may be the cause for the final breakdown in ultra-thin oxides. The exciting news is that there's no breakdown below this threshold, and this opens up a wide opportunity for coming up with devices that you want to have a very long lifetime. Above the threshold, one has to use time, just time evolution to predict lifetimes. You'd need, in an equation, if you're going to use an equation for an engineering approach, you'd need some exponential of the voltage, because there's voltage dependence, some exponential of the temperature, because there's temperature dependence, and then some just time evolution effect. It's not QBD. It's no longer even something that you want to talk about. That's what I claim. And time will bear that claim out. I thank you very much for your attention, and I'll take all questions.
Well, it seems to me that if it's voltage, that means energy, right? QV is energy.
It may mean energy, but not necessarily. I think it may also mean accumulation of holes. Because, let me find a band diagram for you. For example, using a p-type substrate, as you increase the negative voltage on the device, you raise this level right here, you accumulate holes in this region. Applying the voltage accumulates the holes in this region. Now, so what you're doing is you have more and more holes which can attempt to do whatever they're going to do for creating a defect. That's one side, and let me get the other band diagram for you for N-type. For N-type, Well, certainly you have accumulation of electrons, but the threshold occurs when this level here is below this level here. So not only do you have electrons going here, but you may have some holes going in this direction here. And so as you change this voltage, you have a greater hole current going back in this direction. And so I think holes are important, not energy of the electrons, because otherwise I'm not sure how I can explain these thresholds. If it's energy of the electrons, in one case, the energy of the electrons is this from here to here, about 1 electron volt. In the other case, the threshold says that the energy has to be about 2 electron volts. And I can't see why you have a 1 electron volt energy threshold in one case and a 2 electron energy in the other case.
Does the substrate doping have any impact at all?
Not at all. I have looked at, I have to be careful, I've looked for gate injection at substrate dopings ranging from 10 to the 15th to 10 to the 19th. I want to look at really high doping for an application. And the positive charging is the same in those two devices. It just depends on the initial oxide starting quality, I believe.
Was your poly N-type in both cases?
From what I can recall, yes, it was N-type in both cases. However, I've also looked at some undoped poly case, and there, I didn't bring this, I get a different degradation dynamics and a different threshold. And so the doping of the gate plays a role. However, the aluminum gate compared to the N-type silicon gate doesn't seem to make much of a difference. And that's because the interface potential barrier height between the N-doped silicon that's degenerate and the aluminum, and the oxide, and the aluminum of the oxide is about 3.2 eV in both cases. So gate is an important issue.
How about, you haven't looked at P plus gates?
No, no P plus gates. I think that would be interesting, P plus as well as undoped. And also I haven't looked at different gates such as chromium or gold, which would be interesting as well, because I think that that's where we'll begin to get a handle on what this threshold means. Since I got this strange result with the undoped gate, I think that's where...
One other question. Does this positive charge anneal with time after you take the bias off? Is there any... you looked at
Is
that?
there, I guess the question is there any restructuring, any transformation of this? And the answer is there, the short answer is yes. At higher temperatures, particularly at room temperature and above, there's a slight relaxation of this, and we have some papers out on the relaxation of it. And if you anneal it, you can actually make it go away in the aluminum gate devices, but not completely. You usually end up killing the devices if you try to anneal it in polycrystalline silicon gate devices. So there's some thermal aspect to it and some recyclability aspect to it as well.
Do you feel that the degradation thresholds are related to the flat band voltage in any way?
Well, no, because there's no difference in the two doping
You
that I
mentioned
looked
the
at
dopings.
between, say, 10 to the 15th, which gives you 1 flat
Right.
band voltage, and 10 to the 19th, that's about a 3/10 of an electron volt.
What
But the
have you
threshold-
changed from P-type to N-type in the substrate?
Oh, absolutely, there's a difference between P-type to N-type.
In the
But if
substrate
it-
for gate injection?
But if it were related to that, you would also expect to see some change when you went to, say, poly and aluminum. I think it's related to something over in the gate.
Okay.
I'm not so sure if it's just the initial starting condition. I'm not sure if that's exactly it, because there's no difference. I think the strongest evidence for that is that there's no difference for substrate doping in, say, the same doping type.
You made a strong argument that fluence, electron fluence, is not the cause.
Correct.
And I think that was very convincing for a linear term. Can you completely rule out nonlinear terms in the fluence? You might get to a situation where there are very few events that 2 electrons are in sufficiently close proximity to change the bonding in the oxide as they travel through or
Oh,
something.
yeah. That's right. But I don't think that that's okay, you have a good point. So let's say, what case would you be looking at if you wanted to have the greatest probability of seeing that effect. And it would be for thicker oxides, right? The thicker tunnel oxides.
Well, higher fluence in order to turn on possibility of multi-electron
Well then,
effects.
okay, if that's the case, then I think the strongest evidence I have points against what you're suggesting. And that is the case, I'll find it over here. Right here. Data just time. In this case, we're looking at one thickness of oxide, or two thicknesses of oxide. In this case, we're looking at the thicker oxide. And in the thicker oxide, we actually see a decrease in the thickest oxides we've looked at. We see a decrease in this effect. So that means that maybe fluence is playing a role, but maybe it's also just oxide thickness and accessibility and probability. But as you increase the fluence, you're not really doing anything to increase the effect. So I think that there wouldn't be any of this lucky 2 electrons in close proximity, but rather it would be, the data shows that's the least likely of the cases, that you decrease the fluence to affect the effect.
Other questions from both? No, well, thank you again.